In the last video, we took the Maclaurin series representation of e to the x. Now let's do it with a couple of other functions. And we'll see in a few videos that it all fits together like a giant puzzle. Well, let's do cosine of x. So let's set f of x is equal to cosine of x. Well, what's f prime of x? What's the first derivative of cosine of x? Well, that just equals minus sine of x. Minus sine of x. What's the second derivative? Well, that's just minus times the derivative of sine of x. So the derivative of sine of x is cosine of x. So it's minus cosine of x. And what's the third derivative? f3 of x. Well, that's just the derivative of cosine x is minus sine of x, but we already have a minus here, so it becomes positive sine of x. And then what's f4 of x? The fourth derivative of x. What equals cosine of x again? And as we keep taking derivatives, we'll keep repeating, and the pattern will go on, right? The fifth derivative of x. The fifth derivative of this function. Well, the fourth is the same as the function, so the fifth is going to be the same as the first derivative. The derivative of cosine of x is minus sine of x. So hopefully you see the pattern. We're going to do the Maclaurin representation, which is a specific example of the Taylor series where we figure out the values of the derivatives at x is equal to 0. So let's do that right now. So f of 0, let me do another color to fend off monotony. F of 0, well, what's cosine of 0? Cosine of 0 is 1. F prime of 0 is equal to sine of, well, not minus sine of 0, but what's sine of 0? Well, sine of 0 is 0, so minus 0 is still 0, so this is 0. F prime prime of 0. Well, cosine of 0 we already know is 1, but we have a negative sign here, so it becomes minus 1. The third derivative at x is equal to 0. Sine of 0 is 0, so this is 0. I think you might start to see a pattern emerging. The fourth derivative at 0, cosine of 0 is equal to 1. And then the fifth derivative, I know this is hard to read, but you get the point, is just 0 again. So what's the pattern as we take the derivatives? 0, 1, 0, minus 1, 0, 1, 0. So it alternates between 0 and 1. So 1, 0, minus 1, 0, positive, 0, negative, 0, positive. So every other number is a 0, and then between them, we alternate between a positive 1 and a negative 1. So now let's use that information to figure out the Maclaurin series representation. So we realized, we proved, or hopefully, well, we didn't prove that it definitely converges over the entire domain of the function, but you have to take my word for it. And we'll experiment a little bit with a graphing calculator in a few videos. We said that this representation, and it should make intuitive sense, because when you take the infinite Maclaurin series, when you take that infinite sum, you're essentially creating a function where that function is equal to your original function at the point you chose, and in the case of a Maclaurin, we're picking x is equal to 0, and it equals every derivative of this function. So, I mean, just intuitively, it seems like, well, if a function equals something at a point, and every one of its derivatives is also equal to the function at that point, well, maybe those functions are equal to each other. But I haven't proven that to you yet. So we know that the representation is a sum from n is equal to 0 to infinity of the nth derivative evaluated at 0. Right? Maclaurin series is just a specific case of a Taylor series. We actually haven't done anything with Taylor series. I was hoping to get there later. But the Maclaurin series is a really cool one because it's going to show us all of these relationships between e and cosine and sine and eventually I and pi, and you will find it exciting. But anyway, the Maclaurin series is that times x to the n over n factorial. That's what we said it was. So if this is our f of x is cosine of x, what does this turn into? Well, f of x is equal to, well, it equals f of 0 times x to the 0 over 0 factorial. That's just 1, right? Plus, now we're at n equals 1. It's the first derivative at 0. F prime of 0. Well, that's just equal to 0. And who cares with that? But that would be x to the first over 1, right? Now we're at the second derivative. The second derivative at 0 is minus 1 times x squared over 2 factorial plus the third derivative at 0. Well, third derivative at 0 we figured out was 0 plus 0. Who cares what that is? But it would have been x to the third over 3 factorial. And then what's the fourth derivative? The fourth derivative at 0 is just equal to 1. So we have times 1, and then we're at x to the fourth over 4 factorial. So let me see if I can write this a little bit neater. The next one, the fifth derivative, that's 0 times x to the fifth over 5 factorial, and we'll keep going. So let me write this if I can clean this up, and hopefully the pattern emerges if it hasn't emerged already. F of x, which is equal to cosine of x, is equal to, let me just get rid of the zeros, 1, and then we have minus x squared over 2 factorial. This term, so this goes away, this is a 0 term, and then the next one is a positive, plus x to the fourth over 4 factorial. And the fifth term goes away, but then the cycle continues. The next one's going to be minus, because we had minus 1 plus 1, it's going to be minus x to the sixth over 6 factorial. And you could take the sixth derivative, you'll see that the derivative of minus sine of x is minus cosine of x, and that's where we get the minus 1 from. And then we're going to go plus, so we're just taking all the even terms, x to the eighth over 8 factorial minus x to the 10th over 10 factorial. And we could just keep going on and on and on and on. And so we have a situation where we can rewrite cosine of x is equal to the sum, if you believe that this Maclaurin series actually does converge to cosine of x over the entire domain of x. That's kind of an assumption we're making. Hopefully one day we'll have the tool set to actually prove that as well. From n is equal to 0. So what's happening? We're taking all of the even powers, right? So we could say x to the 2n, right? That ensures that no matter what value of n I put in here, I get an even number. So we'll go to the 0th power, then the second power, then over 2n factorial. So that takes care of going from 1 to x squared over 2 to x to the fourth over 4 factorial, 6 over 6 factorial, etc. But now we have to make it switch signs like that. We'll just multiply it negative 1. Let's see what we can do. Negative 1 to the, so we want the first term to be positive, the second term to be negative. So we could say times minus 1 to the n plus 1. Let's see if that works. When n is 0, what's negative 1 to the n plus 1? 0 would be minus 1. And then when it's 1, oh, no. When it's 0, oh, right. When it's 0, it'll be, no. It should just be negative 1 to the n. Right. Because when it's 0, negative 1 to the 0 is 1. When it's 1, it's negative 1. Right, so this is, right, so this will work out. So it's negative 1 to the n is cosine. And you could try it out, right? This is the n is equal to 0. Let me switch colors. That's n is equal to 0, and here we get x to the 0 over 0 factorial, which is 1. And we have negative 1 to the 0 is 1, so that becomes 1. Then when n is equal to 1, this becomes x squared over 2 factorial. And we have negative 1 to the 1 power, so that's where you get the negative 1. And then when n is equal to 2, the negative 1 squared becomes positive again. So the negative 1 is what provides the alternating numbers. So pretty neat. We just figured out another way to represent cosine of x. And it might be looking a little bit interesting to you that this representation, it kind of resembles part of the representation of e to the x. Well, what's the difference between this and the e to the x? Well, e to the x had the odd exponent terms, and it didn't switch signs. But other than that, they're pretty much the same. So in the next video, we'll do sine of x, and then we'll try to put it all together. I'll see you soon.